Today we're looking at strong and weak acids and bases. We've kind of touched upon strong and weak acids back in the grade 10. When we wrapped up acids and bases, or at least those were in my class last year. So just a few things. Strong acids, an acid that dissociates completely into ions in water is called a strong acid. So the idea of dissociation is where the actual compound, the acid itself, breaks apart into its respective anions and cations. Right? So the idea of HCl breaking apart into H pluses and Cl negatives. Right? Now, according to that, so if we looked at the dissociation of hydrochloric acid in the form of so we have the HCl aqueous, and it dissociated into H plus aqueous plus Cl negative aqueous. Right? Whose theory does that follow? The A guy, yeah. Who's the A guy? Arrhenius, right? So we had the Arrhenius. Because what do we not take into consideration with this? Water, right? It's aqueous solution. So where is the water in this, But this is what we mean by dissociation. When you see the term dissociation, and excuse the messy writing, so we're breaking apart into the cations, right? Positive charges, and the anions, which are the negative charges. So all molecules of hydrochloric acid in an aqueous solution dissociate into H plus ions and Cl negative ions. So the whole idea that every single time, every molecule, or every molecule of the HCl is actually going to break apart from itself. It's not going to remain. So that's what the dissociation. So we saw that breakdown. All of them are going to do that. Now, the H plus ions, as we know, as we've talked about, remember, it's just a proton. Remember, no neutrons in the hydrogen atom. Right? So we lose the electron, and it's just a proton. So remember, we know that they don't exist, they don't really exist alone in solution. So they always kind of bind itself to a water molecule, forming this hydronium ion. The hydronium ion, the H3O plus, that is our, let's say, our so-called conjugate acid, as we talked about in the previous chapter. The concentration of hydronium ion in a dilute solution of a strong acid is equal to the concentration of the acid. So if we have 1 mole per liter, okay, or 1 molarity solution of hydrochloric acid, it will contain the same concentration of the actual acid itself, of the actual ion itself, the hydronium ion. Okay, so we have it here in this little table. So if we've put in, let's say, we put in just as a number, just to explain, right? We're putting in 100 molecules, let's say, of HCl in water. All 100 molecules of HCl are going to break apart to forming our conjugate acids and conjugate bases. Right? So we're going to have 100 molecules of the HCl, and we're going to form 100 molecules, let's say, of the hydronium ion and its respective anion, okay, which will represent our conjugate base. So all of them will break apart. All of them will form those ions. And that's what we mean by strong acids. So strong acids, literally all of them will dissociate as such. Here I have an example on the side here of some typical strong acids. So we have hydrochloric acid, hydrobromic acid, hydroiodic acid, HI, nitric acid, sulfuric acid, and perchloric acid. So these are common strong acids, and yes, you do need to know these. So memorize these strong acids. Weak acids. A weak acid is an acid that dissociates very slightly in a water solution. Only a small percent of the acid molecules break apart into ions. So acetic acid, common acid found in vinegar, is considered a weak acid. Okay. as it says here, about 1% of the actual acetic acid will actually dissociate, meaning the remaining 99% remains intact as the acetic acid formula. And I'm going to show you that in just a second. And that 1% translates to 0.1 moles per liter of concentration that will actually dissociate into the respective ions. So the number of acid molecules that dissociate depend on the concentration and temperature of the solution. So of course, as temperature increases, so will the ability to dissociate. Concentration of hydronium ions in a solution of weak acid is always less than the concentration of the dissolved acid. So here we have an example. So before dissociation, here is acetic acid, CH3COOH. When it dissociates, it gives off that proton, that hydrogen proton, to water. I'll give it to water, forming the hydronium ion. And here, if we looked at it in terms of numbers, right? So hypothetically, if we had 100 molecules of acetic acid in water, only one of them will actually break apart. Only one of them will dissociate and give off the hydrogen to the water, forming the hydronium ion, which will leave only one of them, which will remain as its conjugate base. Which means the other 99 acetic acid molecules will remain in its full uninterrupted formula. Okay? So the molecule will appear as is. It will not give off. So 99 out of the 100 will not give off that hydrogen proton to the water to form the hydronium ion. So we're only going to form one hydronium ion. Right? Remember that concentration, as we're going to see, right? The concentration of this is what's going to determine pretty much the type of acid, what kind of a pH level that this acid is going to give. And we're going to get to concentration and pH levels towards the end of this chapter. So a few acids contain only a single hydrogen ion that can actually dissociate. So all the ones that we've looked at, hydrochloric acid, the acetic acid, they only give off one hydrogen. Right? So these acids are called monoprotic acids. So mono meaning one, protic refers to proton. So how many protons can it give, right? Remember, when that hydrogen is given off, right, it loses the electron, positively charged, that proton pretty much tacks on to water molecules, forming the hydronium ion. Right? So as we said, hydrochloric acid, hydrobromic acid, hydroiodic acid. Right? These were three of the examples of the strong acids that I showed you guys in the previous slides. But these are considered strong monoprotic acids. But don't worry about that. Just be able to identify, if I asked you to identify a monoprotic. But you can still name these as strong acids. Right? These are just strong acids. But we know that it's monoprotic because hydrochloric, well, it's H combining with a Cl. Right? So it's only one H with the Cl. One H with the iodine. One H with the bromine. So we can only give off one proton of hydrogen. Hydrofluoric acid, HF, also a monoprotic acid, but it's considered a weak monoprotic acid, or just, we can look at it as a weak acid. So it's similar to acetic acid. Acetic acid, even though it's got the CH3, it can only give off that one hydrogen. So it's also considered monoprotic.